All right, so we're going to go over number 1 through 17 on the chemistry unit 3 review. All right, so starting with number 1. If you have any questions, make sure you ask me. So number 1, number 2, and number 3 are going back to stoichiometry. All right, so you need to go to your notebooks, find this chart if you haven't, if you've done it. Okay, make sure that you're going here. This is the page that's going to be needed, your stoichiometry chart. All right, so number 1 on the questions, you have 2 KClO3 yields or produces 2 KCl plus 3 O2. So remember that the numbers that are in front of each of the compounds, the 2 here, and the 3 here, those are your coefficients. Those are the numbers that are used to balance the equation. So when you're working on stoichiometry problems, you always have to make sure that you balance the equation first. That is also your mole ratio. So if you're asked questions about how many moles of one thing to another, what is the mole ratio for like O2 to KClO3, you're looking at the numbers that are in front. Again, those coefficients. So these are moles. So there's 3 moles of O2 for every 2 moles of KCl and for every 2 moles of KClO3. So this first question says, how many grams of KClO3 are needed to produce 7.5 grams of O2? What you're going to do is you're going to make your list. So number 1, what are we given in this problem? What's our given? Good, 7 points. So my given is, and I'm just going to put a G for given, is 7.5 grams of, and we need to put down what compound we're working with. It's O2. Okay, and then what are we looking for? Okay, so grams of KClO3, that is our question. That's what we are looking for. Now, we are starting with O2. We are converting to KClO3. Are these two compounds the same? Is O2 the same as KClO3? No, they are different. So since they are different, that means in our chart, we are looking at 2 different sides of our chart, okay? So we are starting, one side represents one compound, the other side of the stoichiometry chart represents the other compound, all right? So if we are going from grams of O2, we are starting here, grams of O2. We are changing it to grams of KClO3. So KClO3, since it is a different compound, we need to go to the other side of this line, other side of the chart. So grams of KClO3 are here. Following your lines, how many steps is that? That's going to be 3 steps. So on our paper, 3 steps is 3 lines. We start with our given, 7.5 grams, O2, and it's a 3-step problem. That means I'm going to have 3 lines, times in a line, times 1 line, times 2 lines, times 3 lines. Okay, and then what we're going to do is we are going to fill in those spaces. Now our first line on the paper corresponds with this first line. What you have in the bubbles are the units that are going to go on the line, top and bottom. So you're going to have grams, either on top or bottom. You will have moles on the top or the bottom, okay? We don't know which one's which, but those two bubbles fill in the first line. So we have grams and moles are our choices. We start with grams, so then where would grams go here? On the bottom, because it needs to cancel out. So we have grams of O2. So what goes on top? The other bubble is moles, and it's still moles of O2 because we're still on the same side of the chart, on the left side. All right? Now, looking at the information that is here, what number goes in front of the mole? 1 goes in front of the mole. And molar mass, where do you need to go? So the mass part, where do we need to go to figure out this number? You have to go to the periodic table. All right, so 1 goes in front of the mole. Your grams, you need to go look up oxygen on the periodic table. Look up oxygen on the periodic table. What is the mass of oxygen? 16. It's 16, and we have 2 of them, so 16 times 2 is 32. So we have 32 grams of oxygen. All right, and that's going to take care of our first line. Now, for the second line, this was our first line. This is our second line. That means we're going to have moles on top and moles on the bottom. Okay? So moles on top, we start with moles of O2 here. We're going to end up with moles of O2 on the bottom. And now we're crossing the line. We're going from moles of oxygen to moles of what? Good. So that goes on top, moles KClO3. Mole over mole, okay? 1 goes in front of the mole unless it's mole over mole. And then where do we go to get those numbers? To the balanced equation. So go back and take a look at your equation. The equation was, so we're looking for the numbers in front of KClO3, your coefficients. So in front of KClO3 is 2. And in front of the O2 is what? 3. All right, that line's taken care of. I have moles O2 on top, moles O2 on bottom, so those are going to cancel out. All right, now it brings us to our last line. We have moles KClO3 on top, so where would that go here? At the bottom. All right, this is our third line. We have moles on the bottom, so what goes on top? Grams of KClO3. Okay, 1 goes in front of the mole, unless it's mole over mole. It's not mole over mole, so 1 goes in front of the mole. And then grams, we are going to have to do the same thing that we did with the oxygen. So we have K plus the Cl plus 3 oxygen. So get your calculator out and go ahead and figure out what that is. 122? Make sure you check your calculations. When we get to number 3, you'll be on your own for that one, and that's similar to number 1. All right, so your potassium is roughly 39 grams. Chlorine is 35. Oxygen is 16, but there's 3 of them. So 16 times 3 is 48, plus 35, plus 39 comes out to 122 grams. All right, and then we have the moles of KClO3. Top and bottom are going to cancel out. So the only units that aren't canceling out is grams of KClO3, which is what we're looking for. Take all your numbers that are on top, numbers that are in the numerator, you're going to multiply them together. So I'm going to write it down here. I end up with 7.5 times 2 times 122. And then on the bottom, you're going to do the same thing. If you have numbers on the bottom, you multiply them out. So I have 32 times 3 times 1. All right, so using your calculator, 7.5 times 2 times 122 is 1830. And then 32 times 3, 96. take your top divided by your bottom, numerator divided by the denominator. So we have 1830 divided by 96 comes out to 19.1 units or grams of KClO3. My preference is for this one, we went ahead and we rounded. Depending on the testing format you give, sometimes they round them off, sometimes they don't. So either way is fine with me. You know, I always tell you to go to 2 decimal places, but again, depending on where the test questions come from. That is why when you took, I think, your stoichiometry quiz, your answers were slightly off. It just depended on who was writing the questions, all right? So either way is acceptable. You can round them off to whole numbers, or you can go out 2 decimal places. Any other questions? All right, let's take a look at number 2. So number two says, you have the same equation, and it is asking you what is the mole ratio? What is the mole ratio of KClO3 to O2? So this one, you don't have to do any math, okay? There's no calculations involved here. What is the mole ratio? All you need to do is make sure you keep it in the same order. So mole ratio, again, remember, was the numbers that were in front. So what do we have for KClO3? What's the number in front? 2. And then what is the number in front of your O2? So it is a 2 to 3 ratio. It is that simple. You can write 2:3. Again, depending on the test format, you may see it this way, or you may see it written as a fraction. So this would be 2/3. Okay. Whatever they give you first goes on top. Whatever is listed second, which is oxygen, goes on the bottom if it's written as a fraction. So either version, if it's a multiple choice question, you may see either one of these versions. Any other questions on number 2? All right. Number 3 is another gram to gram conversion like number 1, so I'm not going to go over that one. You do that one on your own. Let's go down and take a look at number 4. Just make sure you leave space. If you haven't already done your work, leave space to work that out. So go down and take a look at number 4. Okay, what causes pressure? Good. Molecules moving a lot. So moving, and then what are they doing? So molecules, they're colliding with what? So molecules colliding with a surface. If you have a lot of molecules and they are doing nothing, they are completely still, there is no vibration, nothing whatsoever, so they're not actually putting pressure on a surface, and it's not going to be, there will be no pressure, okay? So they have to be, it's them colliding with a surface. That causes pressure. Number 5. A says list 3 ways to increase pressure. We want it to get larger. I heard increased temperature. Okay, increase temperature, add particles, and then what else? Good, decrease, so arrow down is decrease the volume. So in all these cases, increasing the temperature, these are all going to increase the number of collisions. So remember that the particles colliding with a surface are going to create the pressure. So the more collisions you have, the more pressure you're going to have. All of these are going to cause an increase in collisions. If you increase the temperature, particles are going to be moving faster, so they'll hit the walls of a container more often. If you add more particles, that means there's more particles to bounce around, all right? So again, there's going to be more particles hitting a surface and creating more pressure. Decrease the volume, you have a smaller space, so that means they will be, as far as the particles, although you haven't increased the speed, you haven't increased the number, the fact is they are going to come up against that wall more often, all right? So that is going to also increase the number of collisions, and that increases pressure. Number 6 was the opposite. It was asking you, oh, I'm sorry, we're not done with 5. 5B, why would these cause an increase in pressure? I actually just answered that, didn't I? Okay, so make sure you have that answer written out. So you should have B, and then make sure you have that answer written out. You need to explain all 3 of them. So question was, do you explain, just like I went through and I talked about each one, A, B, and C, how each of, or those 3 things, how each of them causes an increase of pressure. You need to do that. Okay, so be very thorough. No, we need to, no. You have to write specifically. So yes, don't just write that pressure is caused by, it's caused by more collisions. Yes, that would be fine. Okay, number 6 is doing the opposite. So I'm not going to write this out myself. So those of you who are listening to this video need to be paying attention to what is said rather than trying to skip ahead to the answers. All right, so this is the opposite. It says for number 6A, list 3 ways to decrease pressure. So how will we decrease pressure? Okay, decrease the temperature, increase the volume, and remove particles so there are less particles. B, why would these cause a decrease in pressure? Okay, so more volume means less collisions. If you decrease the temperature, what are you doing to the particles? You're slowing them down. So remember that temperature is a measure of the average kinetic energy, which has to do with motion. So you're slowing them down, which means there will be less collisions. And then your other one was increase the volume. And how does that decrease pressure? Okay, good. So they're more spread out. They have a longer distance to travel, all right, which is going to decrease the number of collisions also. Was there a question? No? All right, number 7 says use your knowledge of molecular bonding and kinetic energy to explain what happens during evaporation. B, what effect would heating have on the rate of evaporation? Why? And C, what effect would cooling have on the rate of evaporation and why? Okay, so you have your different phases of matter. You have solids, liquids, and gases. And when we're talking about evaporation, what is happening during evaporation? You're going from what state to what state? You're changing a liquid to a gas, all right? Now, in terms of those molecular bonding or intermolecular forces, those are the forces, the bonding, intermolecular bonds, the bonding between your molecules. Which of those states of matter, solid, liquid, or gas, has the strongest bonds? Which ones has the strongest bonds? The molecules are tightly bonded together. Which one? Is going to be your solids. And then what's your next one? Liquid. And then your one with the least amount of bonding would be your gases. So what happens is if you're changing from a liquid to a gas, that means the bonds that are holding the liquid together, the molecules together, is going to have to be broken. So in order to break the bonds, right, we're going from a liquid, which is bonded, to a gas where the bonds are broken. What are you going to need to add to this what's going to happen in order for those bonds to break? You have to add heat, which is doing what to the kinetic energy? Making it go faster. Kinetic energy is a measure of kinetic energy is energy that is based on motion. So the faster something is going, the more kinetic energy it's going to have, the more energy it has. All right? So we're going to add energy. So the question was, use the knowledge of molecular bonding and kinetic energy to explain what happens during evaporation. So kinetic energy, when you add heat, you are increasing your kinetic energy. Okay? That added energy to the molecules so that they move faster is going to put stress on the bonds, and it causes them to break. All right? And then when they break, that is when your molecules turn into a gas. Okay? So they change from a liquid to a gas when those bonds are broken. But you need to increase the kinetic energy in order to make that happen. All right? Go ahead and put that in your own words. I'll give you a minute to correct it if you need to. Letter B, what effect would heating have on the rate of evaporation? Rate, how fast it happens. So if you add heat, think about it. If I left a teaspoon of water out, or just put like a couple of drops of water on the table, just put it on my table and left it there, came back tomorrow, do you think that drop of water would still be on the table? How many say yes? How many say no? All right, because it tends to evaporate by itself, yes? Water, if you put a little water on the table, if I come back tomorrow, okay, that's several hours it's going to be sitting here. A drop of water, one drop of water, it will not be there. Have you ever left a surface like you wiped off something? If you go to the restaurant, and they wipe down your tables and it leaves it slightly wet, will that kind of dry by itself if you leave it there long enough? That's evaporation. It's still evaporating, all right? But when do you think it's going to evaporate faster, if it's hot or if it's cold? Hot, because again, when you heat up something, what is it doing to the kinetic energy? It's increasing that kinetic energy. More energy is going to cause it to evaporate faster. So B says, what effect would heating have on the rate of evaporation? Heating is going to actually increase the evaporation because you are giving it more energy. You're adding more energy into the system, all right? It's going to speed up the molecules, and they'll be able to break the bonds sooner. Okay, so I'm just going to move to the screen because a lot of it is just going to be conceptual. So you're going to be writing. Letter C, what effect would cooling have on the rate of evaporation? It's going to slow down it's going to slow down the particles, because what are you doing to the kinetic energy? You're decreasing the amount of energy, decreasing the kinetic energy. So it's going to reduce the amount of kinetic energy in the system, and that will cause the rate of evaporation to slow down. So heating it up speeds up evaporation. Cooling it is going to slow it down. Okay, let's take a look at number 8. Number 8, what is kinetic energy? Good. Kinetic energy is the energy an object has because of its motion. The energy an object has because of its motion. The energy an object has because of its motion. So number 8 again. 8A. What is kinetic energy? The energy an object has because of its motion. Eight B, what is the definition of temperature? Temperature is a measure of the average kinetic energy. A measure of the average kinetic energy. And I'm just going to put KE for kinetic energy. So remember, it's a measure of the average kinetic energy, not what every individual particle is doing. Okay, it is a measure of the average kinetic energy. So if the average kinetic energy increases, what is going to happen to temperature? Temperature will increase. Temperature goes up. The more average kinetic energy you have, if average kinetic energy goes up, then your temperature goes up. On the other hand, D, as average kinetic energy decreases, what happens to temperature? It is also going to decrease. So average kinetic energy decreases, temperature decreases. Okay, so C, if your kinetic energy goes up, then your temperature is going to go up because temperature is a measure of the average kinetic energy. If your kinetic energy goes down, then your temperature goes down. All right, let's take a look at number 10. Number 10 says there are two beakers sitting on a table. Both contain 100 milliliters of water. Beaker A is at number 9. Did I skip number 9? Thank you. Okay, number 9. There are two beakers sitting on a table. Beaker A contains 50 milliliters of water. Beaker B contains 150 milliliters of water. So they have different amounts of water. They are both at 25 degrees Celsius. Which has a greater average kinetic energy? Beaker B? Anyone else? Okay, here's my question. Okay, we're talking about that they are at the same temperature. The question is which has a greater average kinetic energy? Which has a greater average kinetic energy? What is measured? Average kinetic energy is a measure of what? Or what is a measure? Sorry, let me rephrase that. What is a measure of average kinetic energy? Temperature. Are they at different temperatures, Beaker A and Beaker B? So they're the same. They have the same average kinetic energy or the same temperatures, so therefore their average kinetic energies are the same. So it says which has a greater average kinetic energy? Their average kinetic energy is the same because they have the same temperatures. All right, number 10. So in this case, it says there are two beakers sitting on a table. Both contain 100 milliliters of water, so they have the same amount of liquid. But Beaker A is at 25 degrees Celsius, while Beaker B is at 55 degrees Celsius. So remember, we are given temperatures. Temperature is a measure of what? Average kinetic energy. So the question is, which has a greater average kinetic energy? Beaker B. Why? Because it has a greater temperature, and temperature is a measure of the average kinetic energy. 11 and 12, we are still continuing with the concept of average kinetic energy and temperature and how they're related. 11 says a small puddle of water is on a table in a room that is 25 degrees Celsius. There is another puddle of the same volume, so same amount of water, is on another table in a room that is at 45 degrees Celsius. Which puddle will evaporate faster? Puddle B. Why? Okay, it has a higher temperature, which means more kinetic average, has a greater average kinetic energy, which, yes, it will evaporate faster. So puddle B will evaporate faster because the temperature is higher in that room, which has a greater average kinetic energy. Make sure for those questions you always relate temperature to average kinetic energy. Talk about them both. Number 12, 35 grams of wood and 35 grams of copper are sitting in a room which is at 30 degrees Celsius. Compare their average kinetic energies. Think about it. Think about it. Does everyone hear? Everyone understand that? If they are at the same temperature, then average kinetic energies are what? The same. Average kinetic energy is the same because their temperatures are the same. What is the definition for number 13? What is the definition of heat? Good. Transfer of energy from an object of higher temperature to an object of lower temperature. This is number 13. Okay. Heat moves from, if you have an object that is hot and you have an object that is cold, heat moves from hot to cold, which means this is going to lose heat, this is going to get cooler, and this is going to do what? They will even out. But, okay, so while this temperature is going down in this object, what happens to the colder object? What happens to its temperature? It's going to get warmer, all right? So this is basically losing heat to this. It is transferring heat. So this temperature is going to go down. This temperature will go up. They're touching each other. They will eventually have the same temperatures, all right? That's number 13. So number 14, if a warmer object is in contact with a cold object. Okay, we just did this, the same question. If a warm object is in contact with a cold object, in which direction will heat be transferred? It goes from warm to cold or hot to cold. You can draw this for number 14 and then specifically put that it transfers, heat moves from hot to cold. Okay, I just wanted to take a look at this diagram for number 15. Okay, so you already had this in a set of the notes. Just wanting to go over the diagram real quick. Okay, so you have these areas where there's a sloped line, okay? Basically, where that slope line ends and it levels off, you can split those up into different areas. And that's based on what's going on. Okay, so the top line up here, you can't see very well. Let me darken that in. So it goes here, it comes across, and then it goes up like that. All right, so you have a couple of flat areas, and then you have 3 sloped areas. Now, where your sloped areas, sloped lines are, that is where your states of matter exist. So this is going to be right here, is from here to here, that's a solid. It's in a solid state of matter. Where this slope is, that is where you have a liquid. And right here, this last slope is where you have a gas. Okay? Totally solid, totally liquid, and all gas. Right here, what you're having is you have a phase change happening. So if we are moving to the right, changing from a solid to a liquid, that would be called melting, right? If we were moving a liquid and we're changing it to a gas, so I'm moving to the right, that is called evaporation, all right? Now, if I was going backwards, so it depends on if you are adding heat. If I'm moving this way on the chart, you see the what we're doing is we're heating it over time. We are adding heat into the system. Then what happens is it goes from a solid liquid to the gas. On the other hand, if I'm going backwards on this chart, if I'm looking at it this way, then what I'm doing is I'm cooling it down. So it goes from a gas to a liquid and then to a solid. Your points are going to still be at the same point where, but it's just going backwards. Okay, so gas, liquid, we are losing heat if you're moving in this direction. You are gaining heat or adding heat to the system when you're moving this way. All right. So again, phase change here from solid to a liquid, and then phase change here. And I'm just going to write phase with a triangle. Delta means change. There's phase change here and phase change here. Okay. Now, the question in your assignment here, it says, A, is this graph for water? And you needed to list 2 pieces of evidence from the graph that support your answer. Okay, so you had already gone over notes for the phase change. Looking at the graph and the information that you have here, is this water? Is this a graph for water? Okay, I hear yes and I hear no. What are you supposed to, what 2 things? Okay, so look, if I go from a solid to a liquid, all right? If you have ice and you change it to water, what are we doing to the ice? What do we call that? We're melting it, right? So in here is where melting would be happening. If we are changing the liquid to a gas, what do we call that? What are we doing? If we take water and we change it to water vapor, you're boiling it, evaporating, right? Okay, do we know what the boiling point of water is? What is the boiling point? What temperature does water boil at? Not looking at this graph. I want you, based on information, go back to when we went over the scales for Kelvin Celsius. You had 3 things on there. You had the boiling point of water. You had so back when we went over temperature and pressure. In degrees Celsius, what is the boiling point of water? 100 degrees Celsius. Okay, look at the boiling point of water. This is Celsius. Look at the boiling point of water, or the boiling point of this thing. What's the boiling point on here? It says 140. Is that water? You just said, what is the boiling point of water? It's 100 degrees. Is this 100 degrees? So that does not support that this is water. Okay, based on your temperature scales, the temperature and pressure notes, what is the freezing point of water? Or melting point? What temperature? Guys, look at the temperature and pressure notes that I gave you. In degrees Celsius, what is the freezing point of water? It's what? 0. Freezing point of water is 0 degrees. Take a look at the freezing point here. What temperature is this at? Does that look like 0 degrees right here? No? Yes or no? Where I'm pointing right now, is that 0 degrees right here? Sorry, you can't see. I'm pointing at the wrong one. right here. Is that 0 degrees? So this is the boiling point up here. According to this, the substance boils at 140 degrees. Water boils at what temperature? 100. Water freezes at 0 degrees, but this flat line right here for freezing is at about 70. So based on that, what you're seeing here as far as these numbers is this graph for water. No. The reason being, number one, the freezing point of water is 0 degrees, but this is at about 70 degrees. Okay? The second piece of evidence, the boiling point of water is what? 100 degrees Celsius. And for this graph, the boiling point is what? 140. Okay? So again, your question was, it says, is this graph for water? The answer would be what? Is it yes or no? No, it's not. And then list two pieces of evidence from the graph. So first one is, and be thorough. So write out all of that. All right? The boiling or the freezing point of water is what temperature? You need to drill those two numbers in your head. What is the temperature, freezing point of water? What is the freezing point of water? 0 degrees. What is the freezing point on this graph? About 70, okay? So you would write something like the freezing point of water is 0 degrees, but the freezing point on this graph is what? 70 degrees. That's your first piece of evidence, okay? Other piece of evidence. The boiling point of water is what? 100 degrees. And on this graph, the boiling point is 140. Those are your two reasons why this is not water. Go ahead and write your answer. All right, next part. It says, what is happening from D to E? So when it says D to E, that means we are moving this way. You're going from a liquid to a gas. What is happening here? It's changing from a liquid into a gas. Okay, but this isn't for water, so we're gonna stay away from words like steam, because that's normally associated with water. What is the fancy term for changing a liquid to a gas? Evaporation. Okay, so evaporation's happening. And then from A to B, what's happening here? The line is going up. What is happening? To go from A to B, what's happening? Good. The temperature is increasing. Temperature is going up. It's still solid. We haven't changed phase. But the temperature is going up. D, what is the freezing point on this graph? Okay, so to freeze, when you're freezing, you're changing what to what? So to think, just to make it easy, let's think water. When you are freezing, when you hear the term freeze, what are we changing? We're going from what state to what state? Liquid to solid, so that means I'm moving backwards, okay? So where is the freezing point? What temperature is the freezing point? What temperature is the freezing point? So on a graph for water, this would all be at 0. So is it C or B? What's the first point you hit when you're going from a liquid to a solid? C or B? Okay, when you go from a liquid to a solid, which point do I pass first? C. So freezing happens at C. Whether you look at it as freezing or melting, the temperature is the same, but you need to look at which direction are you reading the graph. Are you reading it backwards or are we reading it forwards? If they're asking about freezing, that means we're going from a liquid to a solid. We're reading it backwards. So the first time that we're going to pass that freezing temperature is at C. Now, let's take a look at E. It says, what is the boiling point on this graph? Don't move yet. What is the boiling point on this graph? Boiling point, you're changing what to what? Okay, so I'm reading it this way. So where do I pass? Is it D or E? When do I first get to the boiling point? D. The answer is D. So for number 16, looking at the triple point graph, questions are taking a look at A. For this solid to sublimate to a gas at 194.7 Kelvin, what must be done? All right, so sublimate is where you are changing a you're changing a solid directly into a gas. You are bypassing a liquid. So according to this graph, when you're looking at this line, if you're moving across from left to right, you're changing it from a solid to a gas. You have solid, gas, liquid. So we're changing straight from a solid to a gas. If we are up here, we are changing a solid to a liquid. And if we're along this line, we are changing a liquid, if we go across, straight to a gas. So the question is, for this solid to sublimate to a gas at 194.7 Kelvin, what must be done? Okay, so in order for it to sublimate, go straight from a solid to a gas at 194.7, your pressure must be 101.4, okay, where line meets here, 101.4 kPa. So for A, to sublimate to a gas at 194.7 Kelvin, your pressure must be 101.4 kPa. For question B, it says for gas to condense at 6701.7 kPa, what must be done? So a gas to condense means you are changing from a gas to a liquid. We are cooling it off, we're going backwards, so gas to liquid. And this is happening at 6701.7 kPa. 6701.7 kPa. So along this, and I'm going to actually just go on out to the line here. So where it comes to the line, you're going to trace it down. So at 6701.7 kPa, your temperature needs to be 298.2 Kelvin, probably just a little bit more. This graph is slightly off, but 298.2 Kelvin in order to condense, okay? So to go from a gas to a liquid, change from a gas directly into a liquid, it needs to be at 298.2 Kelvin if the pressure is 6701.7 kPa. The last question for this number, letter C. If I want to boil water, if I want the water to boil at 301 K instead of 298.2 K, so let's go to 301 K on the temperature scale. It says right now it boils at 298.2, but we want it to boil at 301, which is going to be slightly into this area. We want it to boil at 301. What must be done? So what you're going to have to do, and we are boiling, so that means you are changing a liquid to a gas. All right? So liquid can change to a gas going this way, or condensing gas changes to a liquid. All right, so the question is, if it's 301, roughly, what does it need to be? So you're going to have to trace this up. 30, that's 298. Roughly here is about a 301. Roughly, about right there is a 301. So what I would do is trace this up to where it is on the graph, and then you would have to go over. So what temperature is that going to have to be at? All right. So get your temperature there, and this is to go from a liquid to a gas where you're boiling, right? So you're going to need to find out what pressure you need to be at in order for it to switch. So wherever you ended up here, trace it over and estimate what number that is, and that will be your answer for letter C. So 17, it says describe each of the three states of matter in terms of intermolecular forces. We already talked about this a little bit. Intermolecular forces, that bonding. So the strongest to the weakest, the order. Okay, states of matter, solid, liquid, gas. And then you need to draw a particle representation. So somewhere in your notes, I believe you have 3 pictures or pictures that you were supposed to draw. So like where they're really close together and there's a little bit of space, and then the other ones where they're just like all over the place. That's what you need to be drawing for number 17. All right, and then talk about them each, solid, liquid, gas. Make sure you're talking about the forces, the strength of the forces for solid, liquid, gas, and talk about the energy in a solid, liquid, and gas.